The oxide of chlorine. So what did you learn about the oxide of chlorine? Oh, you're telling me what you learned. So Cl2O7 is this formula. Good. Anything else?
It's covalent.
Yeah, it has covalent bonding. It's acidic. Good. Yeah, great. Okay, what about its reaction with water? What does it produce?
Chloric acid.
Yeah, or perchloric acid. What's the formula of perchloric acid? HClO4. Good. And now, because it's acidic, it's going to react with alkalis. In general, what does it react with alkalis to give us? What ion? The perchlorate ion. Which is literally your perchloric acid minus your H plus ion. Is that okay? Okay. So, yeah, then what you really want to focus on and how you can categorize your learning with this topic is by looking at the trends. Okay. So, yeah. As you move across period 3, what happens to the bonding? So what do we start off on the left-hand side of period 3?
What do you mean?
What type of bonding do you have? Ionic, good. And then what happens? We gently progress towards... Yes. Now, I prefer this was off the cuff.
I don't know, off the cuff to be honest.
Well, that's not good enough.
Well, see, only give us a weekend.
And then as we move further right, then what do we end up with?
Pardon? This is advanced level study.
Fully covalent. Okay, and then in terms of structure,
I might just get a chemistry because I wouldn't do the work on otherwise.
what do we start with on the left-hand side? Ionic what?
What's your question?
With structure? Lattice, yeah. Okay, then we progress towards...
No.
Pardon? Giant covalent, good. And then... Okay, molecular covalent. Okay, in terms of where the crossover point is here, should have done this in the previous one. But ionic lattice, that obviously starts with sodium, so let's start with it. Where's your giant covalent lattice? Where's the switchover point here? Silicon, good. And then in the above example, in terms of your bonding, where's the mixed ionic covalent? Which element's that with? Aluminium. Brilliant. Okay, so that's kind of your crossover point, and then once you get past aluminium, you go to covalent bonding. Once you get past silicon, you go into molecular covalent bonding. And then finally, in terms of your acidity / basicity, left-hand side, what's the nature of your oxides?
Basic oxide.
Pardon?
Basic oxide.
Basic oxide, good. Okay, and then we gradually move towards what? Amphoteric. Where's our crossover point for that? Aluminium. And then we move towards acidic. Great. Okay, what I want you to see with this is the link, and it's in there in your notes, is the link between the bonding and the nature of it. So ionic oxides are always basic. Covalent oxides are always acidic. And then if you have mixed bonding, then that's going to get your amphoteric, which is it reacts as acids and alkalis. So you can link the bonding with your nature, and also notice how your crossover point is the same for both of those. Okay, so trends are really important. Also helps you kind of summarise your structure, your bonding, your nature, etc. Right, what else do we want to do? Right, you then moved on to your chlorides of 4 of them, I think it is: sodium, magnesium, aluminium and phosphorus. So sodium chloride, which hopefully you know by now, is NaCl. It's an ionic compound, I assume that is ionic lattice. And we know that our table salt dissolves in water to give us a neutral solution. And just wanted you to notice how that was written. Do you remember back at the time when we did this with lattice enthalpy? We talked about sometimes it's written in the mark scheme plus AQ. And when it dissolves in water, we get our ions. It breaks up into the individual ions. And the aqueous just means that they're surrounded by water. Okay? The harder one is magnesium. Magnesium's reaction with water. So I just want to explain this a wee bit to how we kind of get this happening. So this complex here, tell me what you understand about this complex right now, or did you just look at it be like, what? It's got a charge of 2+, great. Yeah.
Why not?
Okay, so metal complexes, we'll look at them more next module with transition metals. And what we find is that because our metals have an empty outer orbital, we can have these things called ligands attached to them. And that's what the water is. So ligands have to have at least one lone pair that they can coordinate bond to the metal ion with. So what we find with magnesium, hexaaqua magnesium, is it looks a little something like this. So water uses the lone pair on the waters to coordinate bond with the magnesium. So it looks a little something like this. Oh boy. Okay, so for something to be a ligand, it has to have at least one lone pair of electrons that it can coordinate bond to your metal ion with, and it's the fact that the metal ion has an empty orbital, and we'll see that with our transition metals. It's always an empty d orbital that the transition metals have, that the ligands can donate that lone pair of electrons into and form the coordinate bond. Okay, now the reason I have 2+ is because of the magnesium. The magnesium always forms a charge of 2+. That charge on the outside of the formula of the complex, so this 2+ here, that's the charge of the metal plus the charge of the ligands. What's the charge of each of my water ligands? 0. So the overall charge of the complex then is going to be 2+. But what you saw happening is, let me see, go to the next page for this. Okay, what happens is because magnesium has a high charge density, it can polarize one of those water molecules. So if you think of your water molecule something like this, okay, the delta negative sits on your oxygen, obviously, and then the delta plus sits on your hydrogen. Okay, so what the magnesium is doing is polarizing that. And so this bond here between the oxygen and hydrogen is lengthening until the hydrogen actually breaks off. Now we might think that it breaks off like that, but actually the electrons always move to the more electronegative atom. So the electrons move there. Okay, so what am I going to end up with? What's my water splitting up into? 2 ions. Oh my goodness. Yeah, OH minus, the minus technically sits on the oxygen, and H plus. Alright, so now the H plus is floating about, okay, and we're left with the magnesium, with still 5 of the waters. 5 of the waters have been unaffected, but one of the waters has changed to the hydroxide ion. Okay, so bearing in mind that we said that this charge here is the total of the metal ion charge and your ligand's charge, what's the overall charge going to be now? Yeah, it's +1 now. That's because magnesium is +2, your OH minus is -1, and so that gives you a total of +1. Okay, so that's why on the right hand side of that equation you're left with this formula with just a plus sign rather than 2+. Is that okay? And then you've got plus H plus, because that pops off. Is that okay? So aluminium then, your empirical formula, I don't know why I can't say that, is AlCl3, but what does it exist as?
Al2CL6.
Why? Because it exists as a dimer. So Al2CL6, that is one you need to know the structure of. You need to know the structure of that dimer. Okay, when it reacts with water, what do we get a solution of? We get aluminium what? Hydroxide. Good. Plus. Yeah. Okay. Look at this boy here, right? What type of substance is that in general? It's a something something. You're close. So in general, it's a, what is aluminium?
I might know.
It's a metal, and then what's this ending?
Hydroxide?
Yes. It's a metal hydroxide. What does that make it? What does that make it?
I do it there, I do.
What does that make it?
A metal hydroxide?
Yep. Metal hydroxides and metal oxides are all
Basic,
right? So why is it that I'm getting an acidic solution?
Well, that's quite strange, isn't it?
It would be.
The CL or something. I think it's supposed to be a 2.
Apologies.
Happens with bases.
Even more reason for it to be basic, because there's 2 of them. There's twice as many. So why is it acidic if I'm producing something that's basic?
4 times.
Why am I getting an acidic solution, not a basic solution? Think. No.
Hydrogen chloride is acidic, no?
Why?
It's 6H+.
Right. What? Good. So, all acids dissolve in water to give what ions? H plus. What do all alkalis dissolve in water to give? OH minus. Please tell me we know that. That is what makes an acid an acid and what makes an alkali an alkali. That they dissolve in water. So we've got it reacting with water. So we've got something that's basic here and we've got something that is acidic. Why is this not making my solution, why is this not making my solution basic or alkali?
No, but there's no H plus ions there.
There are.
They're not ions.
They are.
No, they're not. You can't do that.
You can because it's dissolved in water.
So wait, what was the question and the answer?
The question was, why does this thing that I've circled in black not make my solution alkaline?
Because it's in a compound.
No. Like if I had sodium hydroxide dissolved in water, I would have hydroxide ions in solution. I need the hydroxide ions to be in solution. So think why it might not be. Keep going. No. What? Yes, but so is sodium. Right, keep going with the solid thing. It's insoluble, right? So you're supposed to infer it.
Okay.
So to make a solution alkaline, you need the hydroxide ions to be dissolved in solution. That's something weird. But with aluminium hydroxide, because it's insoluble, it does not dissolve in water. So I just produce the aluminium hydroxide, but it can't actually dissolve in the water to give me my hydroxide ions. Is that okay?
Yeah.
Whereas hydrogen chloride is soluble in water, so it will give me my H plus ions, which makes it acidic. Last thing we want to look at is the chloride of phosphorus. Okay. Now it does depend whether it's in the solid state or the liquid or gas state. Okay. In the solid state, you see this weird thing happening about one of the PCl5 stealing a chloride ion for the other one. Similar idea with the charges. Okay, phosphorus has a charge of +5 Each of the chlorines has a charge of -1. So what's that total of the chlorines? No, sorry, of the chlorines. There's 4 of them, so -4. Yeah, close enough. So that's why that one has a charge of plus, and then it's why the other one it has an extra. Phosphorus will be +5, chlorine will be -6, and so that gives you the charge of -1. What? Okay, so what holds these together is 1's plus, 1's minus. What do you call that? That holds together oppositely charged ions? Electrostatic attraction. Brilliant. Okay. Right. In terms of its reaction with water, we get phosphoric acid and hydrogen chloride produced. And
like a long division thing or something.
no, it's not long division.
Do you know what I mean?
This is step 1. Okay. The phosphorus chloride, pentachloride, reacts with the water to give us phosphorus oxychloride, I think that's called, plus hydrogen chloride. Okay. Then the phosphorus oxychloride, or that's what we're calling it for now, goes on and reacts with 3 more water molecules to give us phosphoric acid plus more hydrogen chloride. So all that I've done is totaled them. So you've got your, well, better thing to do first is cross out what appears on both sides of the equation. Well, actually, technically that's not true. You need to add them together first. Okay, if we total it up, you've got 1 plus 3 waters on the left hand side, and then you've got POCl3 plus your phosphoric acid.
Can you always do this?
This is a 2-step process.
What do you do? Taking one away from the other?
No, I'm adding the 2 equations together to get the overall equations.
Sure, you have 2 POs. Both opposite sides.
What's this not you?
Right, and then totaling up my hydrogen chlorides, I've got 5 HCl. Okay, now I can cross off what appears on both sides of the equation, so I can cross off my POCl3. So your overall equation you can rewrite as just this. But what you don't see from your overall equation is that phosphorus oxychloride is produced in the interim. So you would just totally miss out on that. Be really sad. For this, yes.